Hey everyone, I am Ms. Hu, your physics teacher. In this video, I will be going through the electricity section of Unit 4 of IGCSE Physics 0625 2023 to 2025 syllabus. For those of you taking this examination, you know that Unit 4 is actually electricity and magnetism, but the unit is really long, so I've decided to divide the unit into two videos. So one video will cover electricity while the other video will cover magnetism and electromagnetism. Otherwise, this overview video will be so long that your brain's going to start leaking out of your ears. So to make this easier, I've decided to put them into two videos so they're a little bit easier to manage. So the segment on magnetism and electromagnetism has been placed in another video. So if you'd like to have the overview on those topics, please watch that video. Now, this is only an overview video, so it's designed for students who have already learned the unit and just need a refresher or a reminder of what's coming out so that they can prepare for their examinations. If you haven't learned this unit and you're learning the topics for the first time, or if you need revision for specific topics in this unit, please watch my videos on those specific topics to help you out instead. Because this is an overview of what's being covered in this syllabus, in this video, we will be making a lot of references to the syllabus guide just to make sure we have covered everything we need to cover. So let's get started. So in this video, we're only going to be covering the electricity segment. So I've pulled these sentences from the syllabus guide. I'm just going to point out to you what you need to know. So you must be able to state that there are positive and negative charges. You have to be able to state that positive charges repel other positive charges, negative charges repel other negative charges, but positive charges attract negative charges. So basically, you just need to remember same charges repel while opposite charges attract. You also need to be able to describe simple experiments to show the production of electrostatic charges by friction and to show the detection of electrostatic charges. So the experiment normally involves rubbing a material with a piece of cloth that is made out of a different material. So for example, you would rub the plastic rod with a piece of wool. The electrostatic charges can be produced through the process of friction. You also need to be able to explain that the charging of solids by friction involves only a transfer of negative charges, which are the electrons. So, for example, if the wool ends up being negatively charged, that means that the electrons have been transferred from the plastic to the wool. Or if it's the opposite, if the plastic is negatively charged, the wool would be transferring electrons to the plastic. Remember that only electrons or negative charges can move. Positive charges cannot move. Now, don't worry, you don't need to memorize which material is more likely to be negative. The question will tell you. So, for those of you who have been doing past year questions and you come across questions which ask you how to induce the charges on a metal sphere. So, the answer scheme would involve bringing a positively charged rod or negatively charged rod near the sphere and connecting the metal sphere to the ground via a wire. If you're like, oh my gosh, I didn't learn this. Well, I've got some good news for you. This has already been taken out of syllabus, so you do not need to know this at all. Let's move on. You need to be able to state that charge is measured in coulombs, so this is the unit for electric charge, and you need to be able to describe an electric field as a region in which an electric charge experiences a force. So that's the definition of electric field. Just going to highlight that. You also need to be able to state that the direction of an electric field at a point is the direction of the force on a positive charge at that point. Now, if you're wondering what this means, this is related to number 10, where you need to describe simple electric field patterns, including the direction of the field around a point charge, around a charged conducting sphere, and between two oppositely charged parallel conducting plates. And effects will not be examined. Now, what this all means is that you need to recognize or draw the electric fields around the charges. So what it means by around a point charge is around a single charge. Just going to go back to the previous slide. The electric field around a point charge is like in this diagram, where around a single positive charge or a single negative charge. So around a single positive charge, you'll find that the lines are going outwards in all directions, whereas for a single negative charge, it's inwards from all directions. If you can remember that positive goes out and negative goes in, it'll be very easy for you to identify or draw the field pattern between point charges or plates. So if we look at these examples between two charges, you can see that if they're opposite charges, the field lines will connect from positive to negative like this. If they're both the same charge, like positive and positive, they'll be going outwards. The arrows cannot connect. That's why they will repel from each other, and the field pattern would look like this, where you don't get any lines joining together. In fact, you get a small area between the charges which have no electric fields. Or if you have a point charge next to a single plate of opposite charge, then they will connect like this. And if you have two plates of opposite charges, then they will connect in parallel lines like this. In addition, you also need to be able to describe an experiment to distinguish between electrical conductors and insulators. So it's really easy. You need to have a power supply and you need to have a light bulb, because then we can see whether the circuit is complete or not. Because if it lights up, that means the circuit is complete. Then we place the material which we are checking between two connecting wires. So if you use an insulator, obviously the light bulb will not light up because the circuit is not complete. Whereas if you use a conductor, the circuit is complete, therefore the light bulb will light up. You also need to be able to recall and use a simple electron model to explain the difference between electrical conductors and insulators and give typical examples. So what they mean in this case is that you do need to remember that electrical conductors are usually metals, and metals always have free moving electrons. So because electrons are free to move, that's what makes metals such good conductors, because conduction of electricity is quite simply the movement of electrons, as we will see on the next slide. Insulators, on the other hand, do not have free moving electrons, so the electrons cannot move, and that's why the current does not flow in insulators. You must know that electric current is related to the flow of charge. This is directly related to the equation. You must be able to define electric current as the charge passing through a point per unit time, and you have to recall and use the equation I equals Q over T. I'm going to highlight that. So in symbol form, you must know, of course, that I is current, which is measured in ampere, while Q is charge, where the unit of charge is coulomb, as covered in the earlier slide, and T is time, which you must measure in seconds. So this is the formula that relates electric current to electric charges. So remember that current is about the flow of charges through the wire. You also need to be able to describe the use of ammeters, whether analog and digital, with different ranges. So normally this would apply more in paper 5 or 6, where you need to be able to take a reading of the ammeter. You need to be able to describe electric conduction in metals in terms of the movement of free electrons. So as I mentioned earlier, all metals have free moving electrons, and that's why metals are such good electrical conductors. Now you also need to state that the conventional current is from positive to negative. So if I were to label the current direction, this is how you can do it. We'll draw an arrow, and I'll label this as I. So current flows from positive to negative, whereas electrons move in the opposite direction, from negative to positive. So to indicate the direction of the electron flow, I'll draw it this way and label this arrow with E to show this is the electron flow. So the flow of free electrons is from negative to positive. You must remember that current electron flows are in opposite directions. Current from positive to negative, electrons from negative to positive. It is easy to remember for electrons because electrons are negatively charged. Therefore, the electrons are in the negative terminal, which then move to the positive terminal. Current is the opposite. Now you should also know that ammeters are always connected in series with the circuit. Now you should know that if you want to take a reading from the ammeter must be connected in series within the circuit. So the symbol of the ammeter is a circle with the letter A inside, and this is how we would normally connect the ammeter within the circuit. So it is in series with the component within the circuit that we want to measure. You also need to know the difference between direct current and alternating current. So direct current is current that flows in one direction only. Just going to write that here. So things like this kind of cell, it is a direct current power supply because the current only flows in one direction. Alternating current, like the term alternating, it changes. Current flows in two directions. So you'll find that alternating current power supply, they don't have any positive or negative terminals because that's constantly changing. So the symbol for an alternating current power supply could look like this. And as I said, there's no label of positive or negative because it'll be flip-flopping. So this side could be positive first and current will flow to the other side, which is negative. Then it changes, this side becomes positive and flows the opposite way to this negative, and so on. So it's always flowing in two directions. So the positive and negative terminals are constantly changing. Let's move on to EMF and PD. So EMF is short for electromotive force. The definition of electromotive force is the electrical work done by a source in moving a unit charge around a complete circuit. And you must know that EMF is measured in volts. The formula for EMF is W over Q, where W is the electrical work done and Q is the unit charge. So EMF is basically how much work done per unit charge to move around a complete circuit. So E in this case is EMF. You can see here the EMF is measured in volts, so the unit is volts. W, of course, is work, which is measured in joules, and Q is charge, where the unit is coulomb. PD is short for potential difference, and it is the work done by a unit charge passing through a component. And if you look at the formula for potential difference, you'll find that it looks exactly the same as EMF. V, in this case, is potential difference, which is measured also in volts. W is still work, which is in joules, and Q is charge, which is measured in coulombs. Now, in case you're wondering, how come these two have the same formula? You should have already learned this by now, but just a quick reminder, electromotive force is the voltage of the source, that means the power supply. That's why it's the work done to move a unit charge around the complete circuit. I'm just going to highlight this just to remind you that, yeah, it's for the source. Potential difference, PD, on the other hand, is only for part of the unit. So for example, a component, like let's say across a single light bulb. So if you have two light bulbs, then the PD across one light bulb is only for that one component. So it's passing through a component only. So PD is the voltage across a component. EMF and PD are both different types of voltages. So remember, EMF is the whole thing by the power supply. PD is just for the component only or part of the circuit. So that's why you find that the formula are the same, because the way you calculate voltage is the same. The difference is that for EMF, it's for the whole circuit, so it's the work done for the entire circuit per unit charge. Whereas PD is only the work done for one part of the circuit across a component only per unit charge. So like for the ammeters, you also need to be able to describe the use of voltmeters, whether analog and digital, with different ranges. Again, this is more paper 5 and paper 6. And to measure the voltage, whether EMF or PD, using the voltmeter, you must know that the voltmeter is connected in parallel to the segment which you want to measure. So if you want to measure the EMF, then you must place the voltmeter parallel to the power supply. Whereas if you want to measure the potential difference across the light bulb, then you need to put the voltmeter across the light bulb. So parallel to the segment which you want to measure. So whether it's across the entire circuit, like across the terminal of the battery, or just for part of the circuit across the component. Right, next, let's go to resistance. So for resistance, you don't need to know the definition, but you do need to know the formula, which is given over here as R equals V over I, where R is the resistance, whether it's a resistance of the component or the total resistance for that segment or the total resistance of the circuit. R just represents resistance. And the unit for resistance is ohm. So you can write OHM or the letter omega, which is the short form for ohm. V is the potential difference measured in volts, while I is current, which is measured in ampere. You need to also be able to describe an experiment to determine resistance using a voltmeter and an ammeter and do the appropriate calculations. So for example, we could have a circuit diagram like this, and this would be an example of an experiment to measure the resistance of this resistor. We have the power supply, which is a battery. We connect an ammeter in series to the resistor and a voltmeter in parallel to the resistor. By taking the readings of the voltmeter for potential difference and ammeter for the current, we use the formula to calculate the resistance of this resistor. So that's a basic experiment which you would need to know. In addition, you need to be able to also sketch and explain the current voltage graphs for a resistor of constant resistance, a filament lamp or filament bulb as written here, and a diode. So just a reminder that if the resistor has constant resistance, it is known as an ohmic conductor because it obeys Ohm's law. So in your syllabus currently, you don't learn the term Ohm's law, but it's useful to remember this. So Ohm's law basically explains the relationship for current and voltage of an ohmic conductor, where the current is directly proportional to the potential difference. And this only applies to certain conductors. So the conductors that obey Ohm's law, they're known as ohmic conductors, and you get a directly proportional graph like this. So the reason why we get a straight line is because the resistance is constant. Because as you can see from the resistance formula, if the ratio of V to I is a constant, you would get a straight line graph just like this. Now, for filament lamps or filament bulbs, we find that the resistance is not constant. So how a filament bulb works is like this. It needs a lot of resistance. So the greater the resistance, the more heat produced, the more light will be produced as well. What happens is it's cyclic. High resistance, more heat. More heat increases resistance, which increases even more heat, and so on and so forth. And why we want more heat? It's because some of the heat will be converted to light. So the more heat energy there is, the more light there would be. As a result, you'll find that the graph for the filament bulb curves this way to show the increase in resistance. Just in case you're wondering how come in this case the gradient is decreasing as opposed to increasing, it's because R is V over I. The gradient of the graphs in this case is the inverse of this formula. Now I'm not going to go into the relationship between the gradient and resistance in this case because we want to keep this video short and sweet. If you'd like to find out more, please watch my video about resistance. Let's move on first to diode. You need to be aware that for the diode graph, it looks like this. Why is it curving this way? It's because diodes are actually electronic components, not electrical components. So the way diodes work to allow current to flow is quite different from the other conductors. So diodes are semiconductors which behave differently from electrical conductors. How it works is that for diodes, there must be a minimum amount of voltage provided before current can flow through. Diodes are unique in the sense that they allow current to only flow in one direction. If connected in a way that current is opposite, it will not allow the current to flow. So that's why if it were the opposite voltage, that means the connection is the opposite, there's no current. Only if we connect it correctly, then current can flow, but it needs a minimum amount of voltage to allow the current to flow through. So that's why you see it like this. So these are the graphs you need to remember for these three different kind of components. Let's move on. In addition, you need to be able to also state qualitatively the relationship of the resistance of a metallic wire to its length and to its cross-sectional area. So if we look at these diagrams just for a quick visual comparison, so remember that resistance represents the obstruction to current in the conductor. So if you have a longer wire, there's more obstruction because you got to think, oh, the charges are trying to pass through. So if the length is shorter, there is less obstruction. Whereas if the wire is longer, there's more obstruction for the current to be able to flow through. So that's why when the length is greater, so I'm going to write in short form here. So when the length is greater, the resistance of that conductor is also greater. Now this is for the core students. For extended students, you need to know that resistance is directly proportional to length. That means that when the length is double, resistance is also double. You also need to know that resistance is inversely proportional to the cross-sectional area, which should be quite logical, right? The greater the cross-sectional area, the more space there is for the charges to be able to flow through, hence less obstruction. That's why the greater the area, the lower the resistance. But for extended students, you do need to know the specific relationship, which is that the resistance is inversely proportional to the area. So if the area times 2, resistance divide by 2. If area times 3, resistance divide by 3. So that's what we mean by inversely proportional. Just be careful though, because this relationship is based on cross-sectional area. Sometimes the question could give you different diameters of the wire instead. So if you have to solve questions with regards to the diameter, while the relationship is still inversely proportional, it's not the same as area. You cannot put, oh, double diameter, therefore resistance is half. This would be incorrect. You have to remember that because area is pi r squared, or in other words, pi d squared over 4, because of the squared nature, if the diameter has doubled, the area has quadrupled because of this d squared. So this then gives us times 4. So the area times 4, therefore resistance is 1 over 4. If the diameter was tripled, that means times 3, then you'll find that it's 3 squared giving us 9. Therefore, the area is not times 4, but instead times 9, which then gives us the resistance 1 over 9. Now I'm moving quite fast here, so if you're a little bit lost, then please watch my video about the relationship between the diameter with the resistance of the wire. That will give you more explanation about this relationship. So for now, just remember that when it comes to the relationship between diameter and the resistance, you have to square the diameter first to get the multiple of the area, and then you use that multiple of the area to get the inverse relationship for the resistance. For now, let's move on. Electrical energy and power. You must understand that electric circuits transfer energy from a source of electrical energy, such as an electrical cell or main supply, to the circuit components and then into the surroundings. You must also be able to recall and use the equation for electrical power, which is P equals IV. I like to call this the Poisson Ivy formula. That's one way to remember it. And you must also recall and use the equation for electrical energy, which is E equals IVT. Just a quick reminder in case you get confused between the formula or you forgot how to obtain the electrical energy formula. Like I said, PIV, I like to say Poisson Ivy formula because that's easy to remember, P equals IV. And the E equals IVT formula is actually derived from the power formula, which, as you should have learned in Unit 1, is P equals E over T. And from here, we rewrite the formulas to make E as the subject, where E equals PT. So because we know P equals IV, we just need to put IV into the formula, and that's how we get IVT. So just in case you get confused or you've forgotten the energy formula, that's how you can work it out. Just a reminder that sometimes you could come across other power formula, which is actually derived from the two formula of P equals IV as well as V equals IR. You could get P equals to I squared R by substituting V into the formula, or if you were to rewrite I as V over R, you would get P equals to V squared over R. So these are two more formula you can use to calculate power. But even if you don't use these two formula, it's fine, because as long as you know these two base formula, P equals IV and V equals IR, you can still solve the question. Now you also need to be able to define the kilowatt hour and calculate the cost of using electrical appliances where the energy unit is the kWh. So kilowatt hour here is actually electrical energy with a different unit. And how you get the kilowatt hour is by using the E equals PT formula, where P is power expressed in kilowatt. That means if the value is in watts, you need to convert it to kilowatt by dividing it by 1,000. And the time is in hours. That means if the value was in seconds, you need to divide by 3,600 to get the value of the time in hours. So once you've gotten the value of the energy in kilowatt hours, you calculate the cost using that energy value in kilowatt hours. So the question would normally give you the value of the cost per unit. For example, let's say if it's 30 cents. So this 30 cents is for every 1 unit. That means every 1 kilowatt hour. So you take the value of the number of units in kilowatt hours times the cost per unit. So that's how you calculate the total cost. This is actually quite simple and logical. So even if you don't remember this, just use your logic. Now let's move on to circuit components. Now you need to be able to draw and interpret circuit diagrams containing cells, batteries, power supplies, generators, potential dividers, switches, resistors, both fixed and variable, heaters, thermistors, which are NTC only, light-dependent resistors, short-form LDRs, lamps, motors, ammeters, voltmeters, magnetizing coils, transformers, fuses, and relays, and know how these components behave in the circuit. You also need to be able to draw and interpret circuit diagrams containing diodes and light-emitting diodes, LEDs for short, and know how these components behave in the circuit. Now in my slide, I do not have the complete symbols for the circuit components, but by now you should already know all of these. Okay, let's move on. For series and parallel circuits, you have to be aware of all these. You need to know that the current at every point in a series circuit is the same. You also need to recall and use in calculations the fact that the sum of the currents entering a junction in a parallel circuit is equal to the sum of the currents that leave the junction. The total PD across the components in a series circuit is equal to the sum of the individual PDs across each component. The PD across an arrangement of parallel resistances is the same as the PD across one branch in the arrangement of the parallel resistances. You need to know how to construct and use series and parallel circuits, calculate the combined EMF of several sources in series, calculate the combined resistance of 2 or more resistors in series, state that for a parallel circuit, the current from the source is larger than the current in each branch, explain that the sum of the currents into a junction is the same as the sum of the currents out of the junction, state that the combined resistance of 2 resistors in parallel is less than that of either resistor by itself, calculate the combined resistance of 2 resistors in parallel, and state the advantages of connecting lamps in parallel in a lighting circuit. Now that's a whole lot of words, and if you're like, oh my god, what is all this? Actually, it's not that difficult. Basically, you need to understand how current, potential difference, and resistance is compared and calculated in series and parallel circuits. So as an overview, I'm just going to use these two diagrams to quickly explain current, potential difference, and resistance. So basically, what you need to know in a series circuit is that the current is the same throughout the circuit. So to visually represent this, I'm just going to draw arrows with the label I to represent current. And in series circuits, you must know that the current remains the same throughout the series circuit. So wherever we place the ammeter, you'll find that the ammeter reading will be the same throughout the entire circuit, wherever we place the ammeter. Whereas for parallel circuits, because the circuit branches out, you'll find that the current is not the same. So the current that flows out of the dry cell will of course be greater than what's flowing in the individual components in the parallel circuits. Because what happens is when the current reaches the branch, when it splits, we get 2 different values. And then they will join back together to here again. So you'll find that, let's say if I label this as I3 and the current in R1 is I1 and the current R2 is I2, you'll find that I1 plus I2 will give us the value of I3. What we start with is the same with how much we finish. This is I3, by the way. So that applies for the series circuit as well. Whatever we start with is whatever we finish with. So for parallel, whatever we start with is whatever we finish with. But I3 will of course be greater than I1 and greater than I2. And I3, how we calculate it, it's the sum of I1 and I2. Now for potential difference, if we represent this with the voltmeter, now I'm going to label the voltmeter across R1 as V1 and the voltmeter across R2 as V2, and the voltmeter across the battery, the reading will be V3. Because potential difference is the work done to move a unit charge, you can see in a parallel circuit, V3 is not across a battery actually. V3 is across the entire circuit from here all the way through to the other end over here. So V3 includes V1 and V2. So V1 plus V2 will give us V3. However, for parallel circuits, we find that because of those branches, the work done through one branch has to be equal to the work done across the other branch as well. So even though they're different lines, V1 and V2 would be equal. So as you can see from the circuit, if there are no other components in the circuit, then the voltage across the battery would be the same as V1 and V2. Now, if there were other components, they wouldn't be the same. But for now, we're just going to look only at the components that are in parallel to the battery. There are no other components as shown in this circuit. That's why in this situation, V1, V2, and V3 are all equal. In terms of the calculation of the total effective resistance, just remember that for series circuits, it's very logical. The more resistors you add, the higher the resistance would be. So the total effective resistance, which I'll label as R, is just the sum of the two resistance in series added together. However, for parallel, it's the one that's more confusing. You cannot just add them together. So the formula is 1 over R equals 1 over R1 plus 1 over R2. If you've forgotten why, please watch my video about the resistance calculations in parallel circuits. Next, let's move on to potential dividers. What you need to know is that the PD across an electrical conductor increases as its resistance increases for a constant current. And this can be understood quite simply from the V equals IR formula, where if we rewrite I equals V over R, if I was constant, therefore when V increases, R also increases. So mathematically, you should already understand this. So for this, normally we'll find potential dividers in series circuits because it's only in series circuits where the current is constant throughout the entire circuit. You need to be able to describe the action of a variable potential divider and recall and use the equation for two resistors used as a potential divider, where the formula is given as R1 over R2 equals V1 over V2. So just to quickly remind you about potential dividers, it is based on the understanding of series circuits, because if the resistance increases, obviously the potential difference also increases. So if there's lower resistance, then the potential difference also decreases. And why this is true is because in a series circuit, like I said, the current is the same. So if resistance increases, this causes the potential difference to also increase based on the VIR formula. So this formula is actually derived from the I equals V over R formula, because if current is the same, therefore V1 over R1 equals to V2 over R2 for those individual sections on the circuit. So if you rewrote this formula, putting R on one side and V on the other side, that's how we can get this formula. So this is the foundation for how potential dividers work. So the potential divider is actually any resistor that functions to divide the potential difference. So for example, if the current given here in this circuit is say 1 ampere and the resistance of R1 is 1 ohm, that means V1 would be 1 volt. Whereas if R2 was a different value, say for example 2 ohm, then V2 would be 2 volts. So you can see in this case, the different resistance values already divide the potential difference. So if the battery was 3 volts, the resistors have divided 3 volts into 2 volts and 1 volt. So that's what we mean by potential dividers. So if we want to be able to manipulate the potential difference more easily, we would use a variable potential divider. Usually this component would be a variable resistor. So for example, we could use a variable resistor like a rheostat, because a variable resistor can change the resistance. Let's say you can change it from any value between 0 to 2. So by changing the resistance, we can change the potential difference that has been divided within the circuit. The change in V1 would cause a change in V2. So for example, if this was 3 volts, if you change this down to 1, this becomes 2. If you change this up to 2, this becomes 1. So the variable potential divider not only changes its own potential difference, but the potential difference across the other components in the circuit as well. So that's why we use potential dividers. Like I said, this is just an overview. If you need more information, please watch my video on potential dividers. And the last topic on the electrical segment in this unit is on electrical safety. You do need to be able to state the hazards of damaged insulation, overheating cables, damp conditions, and excess current from overloading of plugs, extension leads, single and multiple sockets. So you need to be able to describe what the hazards are and explain what could happen as a result of this. There have been past year questions where you need to be able to state what the dangers are in this case. And this is something you should already know by now because it's logical and it's something we should be aware of on a daily basis anyway. You need to know that a main circuit consists of a live wire, a neutral wire, and an earth wire, and explain why a switch must be connected to the live wire for the circuit to be switched off safely. So in case you have forgotten, remember that the brown wire is the live wire. So you of course must know the live wire is connected to the fuse, which is then connected to the entry point of the socket. The blue wire is the neutral wire, whereas the wire that has the green and yellow stripe, that's the earth wire, which is connected to the ground. The neutral wire is the one that completes the circuit together with the live wire. You need to be able to explain the use and operation of trip switches and fuses and choose appropriate fuse ratings and trip switch settings. So the trip switch is the circuit breaker where it trips if there's too much current flowing in, whether it's due to a lightning strike or if there is a faulty device that's been connected within that zone. For the fuse ratings, always remember you must select a fuse rating that is higher than the value of the current that is needed to operate the appliance. Because if you select exactly the same value or lower, then the fuse is always going to melt and stop the current from flowing. That prevents the appliance from working properly altogether. So for example, if the appliance needs 8.33 ampere, you must select a fuse with a higher rating than 8.33, usually about 13 ampere. So if you're wondering, is it okay to select such a high value? Yes. Usually fuse ratings are fixed values. You can't pick, 8.33, therefore I pick 9 ampere. It doesn't work that way. There is no 9 ampere fuse. 13 ampere is okay because even though the appliance needs 8.33, normally the appliance is designed to be able to work safely up to 13 ampere, which is the next highest value for the fuse that is available in the market. By the way, you also shouldn't pick something just above, like if it's 8.33 and you pick 9. We don't normally pick a value that's so close to the value needed because in case there's a slight surge, then what happens is a fuse melts, then it can't work. So that's why normally we pick something that's higher, like high enough that it's not too high. You can't pick something like 25 ampere. So you don't pick something that's much, much higher, just the next highest normally, if that makes sense. You also need to be able to explain why the outer casing of an electrical appliance must be either non-conducting, double insulated, or earth. So that's because it is to prevent the current and charges from moving to the surface of the appliance, which could be touched by a human being or an animal and get shocked. So that's why it has to be either non-conducting or earth. And you need to be able to state that a fuse without an earth wire protects the circuit and the cabling for a double insulated appliance. So what this means is that sometimes you could get plugs that have only 2 pins. That means they don't have an earth wire, only the live and neutral. So you must have a fuse, and it protects the circuit and the cable, and the appliance must of course be double insulated to prevent electrical shocks. And that's it for the electrical segment. So if you found this video to be educational and helpful, please subscribe for more free physics lessons. And if you're feeling generous, please help me keep making free educational video lessons and lab practicals by donating at ko-fi.com/physicsrocks. And if you'd like notes, quizzes, and syllabus updates, please visit my website at physicsrocks.com. To all the students taking their examinations, happy studying and all the best for your exams.